Now, in this lecture, we're going to come up with really a wonderful solution to that networking problem that we were looking at in the previous lecture. Let me restate the problem. Given a weighted connected graph, find the spanning tree of least weight. Over on the right, we're looking at an example that we've looked at before. This is the Ohio State campus graph, in which the weights represent the distances between pairs of campuses, and we were thinking of those as costs that would have to be incurred if you were going to build computer network connections by choosing those edges. And here is one example of a spanning tree. We were wondering, is this the spanning tree of least weight? Well, here's an algorithm that one could use to solve the problem. Step 1, list all the possible spanning trees. Step 2, for each spanning tree, compute its total weight. And now, having a list of all possible spanning trees and all total weights, let's choose from the list the spanning tree of least total weight. Now look, this is a terrible idea. We've thought about this very same kind of algorithm before, not in connection with this problem, but similar sorts of problems. And right away, there should be a red flag going up as soon as you see what step 1 is, because it says list all possible spanning trees. Now look, a complete graph has lots of spanning trees. As we've already said, the one shown over on the right has 1,296 spanning trees. So if you were going to use the proposed algorithm to solve this problem, step 1 would say list all 1,296 spanning trees. Now this is a small example. This is the complete graph on 6 vertices. If you would have the complete graph on 7 or 8 or 9 vertices, then you get many, many spanning trees. The formula is n raised to the power n minus 2. Let's just see how that number grows. If you have 5 vertices, which is the number that we have in the Ohio State campus graph, already there are 125 possible spanning trees. It already seems a rather unpleasant task to actually have to list all of those spanning trees, compute their total weights, and then finally pick out the best one. For a complete graph on 6 vertices, we've seen it's 1,296 spanning trees. For a complete graph on 7 vertices, 16,807. And let's go all the way up to 10, which is really not a very large number, right? Number of vertices is 10. You could easily draw the complete graph on 10 vertices, but you would not want to list all the spanning trees because, according to our formula, there are 10 to the 8th, that is to say 100 million of them. Okay, so this algorithm that's been suggested, in which step 1 is to list all possible spanning trees, is just a terrible idea. This is our brute force algorithm, and it's not at all a practical algorithm because making that list is just really a practical impossibility. Fortunately, it turns out that for this problem, not only is there a simple algorithm, but an algorithm that really solves the problem. There is a wonderful algorithm that is called Kruskal's algorithm, and it's really a perfect algorithm from all points of view. First of all, as I've said, it really solves the problem. So unlike what we saw in the traveling salesman problem, this is not an approximate algorithm. This is an algorithm that really finds the spanning tree of least total weight. The second thing that's nice about it is it's very easy to state. It will be on the next slide. You'll see what it says. Another thing that's nice about it is it's actually easy to use. It's not a hard recipe to follow. And the last thing is it works efficiently. So really, you can't ask for more from an algorithm. And what does it say? Well, here it is. It's that sentence up at the top. It simply says, repeatedly choose from the entire graph the edge of least total weight that doesn't create a circuit. So how do you get started? Well, you look at the whole graph, and since you haven't chosen anything yet, you choose the edge of least total weight in the entire graph. There's no possibility at this point of creating a circuit. So then you go on and you say, well, what's the next lowest weight? Okay, and you choose that edge too, and on and on and on, always looking at the edge of least total weight. Now, you don't always take it. You see, you have to decide whether to reject it or accept it. But the only reason for rejecting an edge is if it creates a circuit. If it creates a circuit, then don't take it. Otherwise, do take it. This will remind you of an algorithm that you used in the traveling salesman problem, namely the cheapest link algorithm. There, the algorithm, which sounds very similar, had slightly different instructions for when to reject an edge. Here it's actually simpler. Okay, again, reject an edge in Kruskal's algorithm if it creates a circuit, otherwise accept it. Now, you might wonder, well, how do I know when I'm done? Well, my answer is you'll have a spanning tree. If you don't quite like that answer, remember that the number of edges you want is one less than the number of vertices in the graph. So you know from the very beginning, looking at the number of vertices, how many edges it is that you want. You want one less edge than the number of vertices. So let's look at an example. The example I want to look at is the Ohio State campuses. Okay, now I'm already showing you the final answer, but let's see how we got to this. How did we discover that this is the spanning tree of least total weight? Well, here's what you do. You look over the graph and you ask yourself, what is the edge of least total weight? And the answer is it's the edge from Marion to Mansfield, and that weight is 38. So you draw that in. What's the next lowest weight? The next lowest weight is 40, and that one's also okay. This is not creating a circuit. And the next one is weight 50. Again, when you take that, you haven't created a circuit, so that's your third edge. And then the next lowest weight is 54, and again, this doesn't create a circuit. And now, since we've selected 4 edges, that's it. Okay, and there you see it. We have a spanning tree consisting of the 5 original vertices together with these 4 selected edges. Now I've got to say, having gone through that example, it's not a good instructive example. And why not? Well, because we never saw why it is that you might have to reject an edge. It just so happens in this particular graph, if you take the 4 edges of least total weight, they form a tree, and that's the one you want. It's the spanning tree of least total weight. In your recitation, you will have examples where you really do have to sometimes accept and sometimes reject.